Okay, let me quickly hand in the midterm, just for nothing else for me to learn your names. Fartin, okay, Sirit, Sahuratin, Secret, no, okay. Valerie Chang, okay. Amin, Mitchell Cow, Mingong Kim, Andrew Chang, Stephen Lanziera, Radford Big Zhuang, Radford Ray Wang, Liying Chang, Liying Chang, Portia Jones. That's you? Okay. Jingua Wang. Could you pass this on over there? Ted Lee. Sean Koo. Joyce Liang. Alan Gu. Oh yeah, there's a two-part thing. You're right. Hey Cam. There's one without name. That you never figured out who it is, did you? Or is it the person next to Aaron Floyd?
Oh yeah, sorry. This is
That's okay. Aaron. Okay. Aaron Floyd. Okay. Did you hand in this as well?
Yeah, I also handed it.
And did you look at the?
Same question.
Yeah, I wrote on the first one.
Okay, very good, very good. Sandy Pan. Where's that? Okay. Could you pass this on the way? Omar Bach. Andrew Hatch. You got two of them. Sue Gion. Okay. Matthew Moo. And Sridhar Mishra. Okay. Jacoby Hicka. Sutong Chin. Kineet Gupta. Evan Chow, C-H-A-W. Peter Sang. Uday Reddy. Uday. Marianne Varus. Bharat Sinha. Jian Hu Zhang. What's this? Kevin Wang. Kevin, are you here? Ann Nguyen. Hey Nguyen. Honey Wong. Uzon Powell. Carson Wong. Zucker. That's the photo. It's here. Li Yang. Qiaolin Zhang. Tina Shen. Liang Tik Pang. Jonathan Sao. And Ruth Wang. Nicole Wrong City Acorn. Nicole. Alan Sao. So you learned yesterday, right? All right, I remember you. Once Up Sim. Yeah. You're Tiffany, right? I don't think I read your name. Oh, what? Okay. It's possible. Did anybody else by accident get Tiffany's? There's only one guy somewhere in the middle, like yours was not stapled. Did Tiffany's come with that? How did you have? What happened? Okay. Don't have much of an explanation for that. And this is your graded homework also. Okay. So I think that overall you did okay. I mean, there are times that people didn't complain nearly as much as you did, and previous times I taught the course, and the average was still 70. In fact, 70 is like right on. That's exactly how you want it to be. You don't want the average to be 95. You don't want it to be 35. You want it to be somewhere in the between 60 and 80 or 70 range. So I think I'm pleased with the results. If you have any questions regarding grading, go see Dan Hazen, the TA. If you have any other concerns, come see me. Yeah.
Do you have any idea of the distribution of those scores? Around 75 online?
The highest grade was 95, sorry. And the lowest grade was 33.
What was the median?
Didn't compute that. Yeah. I think I answered that question at the beginning of the semester. There's usually not a need, but if there is a need, I will do that. Do I grade undergrads and grads separately? Come up with a different curve.
It's not a good idea.
Thank you for your comment. Okay, any other issues? Yeah.
Wait, we get average, so does that mean you get a B plus or a B?
I can't say that at this point. What I do is I plot a curve, and there's certain percentages for A, B's, and C's, so I take that into account, but those percentages are not fixed. So those percentages together with the gaps in between the bumps, that determines who gets A, B's, and C's. You want to have some measure of fairness. Ideally, two people who score very, very close to each other, you want to get a similar letter grade. So that's one consideration. And then the other consideration is the department guidelines of what percentage get A, B's, and C's. So it all depends on how the final bump looks like, the histogram looks like.
What's the department policy?
I don't have it with me here. There's a certain guidelines. You don't want to give A's to 1% of the students. You also don't want to give A's to 90% of the students. It's there's some distribution there. Okay?
Thanks.
All right. All right, I know this sounds like a cliche, but I think in general it's good to be concerned about learning the material more than... I have to say that like 90 times a night to my son, who's only 10 years old, but It's amazing how the advice remains constant from a 10-year-old to a 22-year-old or 25-year-old or whatever the age is. So I think I'm quite pleased with the performance of the group as a whole. Yeah.
Can you possibly make the next midterm a little shorter in length?
I will try. As I told Dan when we were making this one up, we knocked out a question last minute. It was going to be long. I mean, I did bring up, I mean, Dan probably can witness this. I did tell Dan we don't want this to be a speed test. So, and I'm fully aware of it. So, on the other hand, I think that, you know, I didn't want to have, you know, it's good to have some sort of a differentiating factor, although I don't want it to be speed. I want it to be sort of understanding of the material. But I will take that into account. I think now that I'm calibrated against Dan, if he says it takes 40 minutes to do it, I think it's too long for the rest of you. Mm-hmm.
Like also, Dan emphasized that we had to explain our answers very carefully. So I took a lot of time to explain things in great detail. So I don't know, really to what depth you expect.
Well, I don't want, because there was a lot of questions that had yes and no answers, I didn't want to get yeses and nos. I wanted to have an answer that justifies it. So you probably notice that if you just, is the system causal or stable, yes or no, even if it was the right answer, if you didn't explain why that is, you probably didn't get full credit for it. So that was sort of one issue that came up. You did notice that there was no question on filter implementation or filter design. That's because there was no question on that. There will be some emphasis of that in the final. That was the question that got bumped off. There was 4 questions initially. I thought it's too long. We bumped that one off. We divided the points for that among the rest. So as a result, you haven't really been tested on, I don't know, filter realizations and FIR filter design or any of that, even though, technically speaking, it was part of the, the first midterm. So I'm just telling you that there'll probably be more emphasis on that at the final exam, or the second midterm, if you will. By the way, the second midterm is on December 5th, 9:30 to 11. Probably also in Sibley Auditorium, but I'll keep you posted about the place. Yeah.
So does that mean that the second midterm is cumulative, like you add up?
Yeah, it's not just from the middle of the course to the end. It's cumulative with more emphasis on the second half. But I don't want you to have forgotten important things like Fourier transform properties and Z transforms and other things, and upsampling and downsampling and those other issues. Any other questions or comments? Yeah, I think I must say overall I'm very pleased. I thought the exam was hard, and I heard you complain, so I was very worried that mean is going to be like 30 or something, but it didn't. So I think you guys are doing good. So I'm pleased with that. Okay. Is there any other? Yeah, one more.
Do you have what's the computer average for just the undergrad alone?
Computed average for undergrad? I don't think I.
That 70 is the overall,
Right. No, I don't have that number. So. Okay, so what I'm going to talk about now is Okay.
So there's a typo in question 737, I think.
In the book.
In the book, yeah.
Okay, let me write this on the board.
So hopefully I can remember it here, but the definitive source is going to be on the website. It's been posted on there. But I think what's been changed is we changed the capital HD definition. It says the Fourier transform of H of n is HD of e to the j omega, and then it sets it equal to something. Change that to H. And then for parts B and part C, change the lowercase hd to H. And it's posted on the website.
How'd you know there's a typo?
Because the question doesn't make sense with the wording the way it is.
You've done the solution to it?
Yeah. Well, yeah. I mean, I've not written it out, but yeah.
Okay. Okay. So what I'm going to talk about today's lecture is IIR filter design. So we've talked about FIR filter design at quite a depth. We talked about window, talked about optimal, and what I'm going to talk about now is the two main techniques for designing IIR filters. Okay. And just as a bit of a preview, we're only concerned about designing IIR filters that have a rational transfer functions because those are the ones that can be implemented using difference equations. Okay. So how does IIR filter design work, and what do we mean by IIR filter design? The first thing that you might say is that if you're trying to design an infinite impulse response, it has infinitely many non-zero values. So how can we ever design infinitely many values for any filter? And the answer is we're going to restrict our attention only to IIR filters with rational transfer functions. And as soon as you do that, then the problem becomes meaningful. And what do I mean by that? Well, if I'm designing an h of z, which is a ratio of two polynomials, p of z over q of z, each one of these guys are polynomials in z, then p of z, for example, is summation over n, a of n, z to the n. That's what I mean by being a polynomial in z. So essentially, filter design reduces, where this summation is not infinite. This polynomial has finitely many terms, you know. N equals, I don't know, 0 to capital N or something like that. Then the filter design reduces to determining these coefficients. Okay, so filter design is equivalent or the same thing as determining these coefficients. Okay, the same thing with Q. If I have Q of z is the summation over n of b of n z to the n, then I have to design A of n and B of n. That's an array of numbers. Okay? And what can we say in particular about designing these things? Well, we're going to talk about two different techniques for coming up with A's and B's. Okay? So one technique is basically just direct technique of solving things numerically. So that's you stay in the discrete time domain, and I'll explain that in maybe 2 or 3 lectures from now. But the technique we're going to start talking about today is what's referred to as the transformation technique. And as I said in the last lecture, what it boils down to is reducing the problem to an analog IIR filter design, and then converting that analog filter into a digital filter. And there's 2 classes of transformation techniques. There's impulse invariance, and then there is bilinear. Okay? And today I'll talk about impulse invariance. Probably on Friday I'll talk about bilinear. And then we'll move on to the direct numerical technique. So let me, before moving much further, let me outline the 4 steps. Let me just talk about the transformation technique in generality before I dive down into the details of how impulse invariance and bilinear techniques work. So there's really 4 steps to the transformation technique. Okay, step 1 is that you're given a certain set of digital filter specs. So given a set of, and remember I use here digital, what's it called, interchangeably with discrete time. So digital and discrete time here means the same thing. So I'm given some sort of a filter spec in the discrete time domain. And then the second step involves transforming these specs from discrete time to continuous time. So digital is the same as discrete time. So I'm going to transform, that's why it's called the transformation technique. So I'm going to transform the specs from a discrete time into continuous time. And now I have a set of specs in continuous time, and I go ahead and design an analog filter in continuous time. So again, I'm using the word analog and continuous time interchangeably here, but so we want to design a continuous time filter, time IIR, which is the same thing as analog filter, which I call H sub A of S, and A here stands for analog. So continuous time and analog have the same meaning, okay? And I think I've already gone over this discussion as to what are some techniques people use to design a continuous time filter. What are some, not techniques, implementation ways of designing analog filters? And we went over RC design. You can have passive circuits. You can have active circuits. Active circuits are the ones that have transistors, and transistors can be put together to have op amps. So those are, so you can design your analog filters using those type of things, or using R's and C's. And actually, we have a sizable number of mechanical engineers in this class. You can also have mechanical filters, right? What elements, who are the mechanical engineering folks? Maybe you can raise your hand. I won't call upon you specifically, just to know whether we have any. We do have 3 or 4. But what are some ways of designing filters in mechanical filters? What is the equivalent of RLC, resistors, capacitors, and huh? Yeah, mass. What's it? I know about springs, but what's the other thing? Dampers. And what else? And boxes, you said? No, it's a mass spring and mass springs and dampers. Oh, all right. So could you relate that maybe to RLCs? So a damper, we hear from this end of the room, the damper is a inductor, is equivalent to an inductor. A mass is equivalent to a capacitor, and a spring is equivalent to a resistor. So you can have mechanical sort of filters, right? Does that sound right? Actually, I don't know.
A damper is a loss element, and so it's equivalent to a resistor.
Okay.
And a mass is a storage element, so it's a movement storage element. So I'm guessing it might be an inductor. I'm not sure though.
Mm-hmm. Well, in electrical engineering, an inductor and capacitor are both storage elements, right? One stores current, the other one stores charge, right? Right. Well, I mean, one of them resists having its voltage changed in an instantaneous way, which is capacitor, and inductor resists in having its current change in an instantaneous way. So in that sense, they're both storage elements. But I guess one question I have, and maybe the mechanical engineering folks can clear that for us. Like in electrical engineering, it's like input voltages that go in, and then an output voltage comes out. In mechanical engineering, what are the typical examples of an input and output? It's some sort of a motion goes in and a motion comes out, or what is? Force is excitation goes in, and what comes out? Displacement and velocity of response. Okay.
It's actually the other way around, because usually, if you say a voltage is across something, a velocity is also across a system.
I see.
Current through a system, so force through a system.
Got you. Okay. Okay, very good. So a lot of these concepts cross over from electrical to mechanical engineering. But anyway, there's a body of knowledge about how to design these analog filters, and then once you have your analog filter, you can then transform it into this discrete time filter H of Z. So this is a transformation from continuous time into discrete time. Okay. In other words, from the S domain to the Z domain. Okay. So before I dive into the details of this and give you examples and clarify this page, I want to spend a minute talk about continuous time IIR filters. And as I said earlier, when I was an undergraduate, there would be an entire quarter or maybe 2 quarters worth of class on continuous IIR filter design, continuous time IIR filter design. And the classic book for it is Lamb. And the professor actually was Hardy Martel, who was at that time a chain smoker. He would never put out any. He would literally extinguish one and start the other one. We never had like a minute of no smoke, but those days are gone. And so is continuous time filter design. They're all. But the guy was very smart. You know, anything you asked him, he just had a catalog of all possible filters in his head. And said, "Oh, you can do it like this, or you can do it like that, or you can do it like this," and it's just things came out very rapidly out of him. I wonder if he's still alive. All that smoke, I mean, non-stop. In the lecture room too. Anyway, well. In case you needed to know, I was a smoker too at that time, so I shouldn't. Maybe I became a smoker because of the professor, but let's not blame him too much. But continuous time IIR filters. Okay. Yeah, you basically, you used to go to vending machines to get Coke, and the cigarette machine was right next to it. And in case you wanted to know, it was only 75 cents when I was an undergraduate. And what is it now? Do we have any smokers in this class? You won't get discriminated against. I think it's. I quit a long time ago, but I think it's like $4.50 or $5 or. Every time California gets into budget crisis, the tax on cigarettes just keeps going up, which is a good thing. Hopefully, it's a deterrent for you guys not to ever get started. But anyway. I mean, with $5, you can buy like 10 Snicker bars or something, right? I mean, it was right next to the Snicker machine. I had my dollar bill, and I would get the change. Okay, 3 quarters. I can either put it and get a cigarette, or I can get a Snicker bar. Well, I get a cigarette. It makes me lose weight or something. All right. Let's not get distracted here. So, what are these continuous time IIR filters that Hardy Martel taught me when I was an undergrad? So there's the Butterworth filters, and I'm sure actually we teach that in our own undergrad curriculum, right? Do you guys, do our undergrads learn about like Butterworth filters and Chebyshev filters and elliptic? How about any other person in this room? I'm
thinking 120, actually 145L.
You learn it in 145L,
Could I just point out that anyone who might want to study it, it's Appendix A of the book.
Good thinking. Is it in the Appendix A? I didn't realize that. Fantastic. Okay, so it hasn't entirely evaporated. It's now in an appendix. But so Butterworth filters. Butterworth is the name of the guy who invented it. They are monotonic. What it means is that if I plot the magnitude of this analog filter as a function of omega, and notice I'm using capital Omega now to denote that I'm in continuous time, okay? So it's monotonic in passband and stopband. And I'm limiting the discussion to low-pass filters. So it's monotonic in passband and stopband. And then the second category of filters that you have are Chebyshev, which is the same Chebyshev we talked about Chebyshev trigonometric polynomial and Chebyshev inequality and all those other things that this Russian guy came up with. And Chebyshev filters, they have a ripple in the passband, or in stopband, but not in both. So they could have some sort of a ripple like that and then come down like this, or they could have monotonically decreasing in the passband and then some sort of a ripple in the stopband as a function of omega. So this is magnitude of h sub a of omega, magnitude of h sub a of omega. So they either have a ripple in passband or in stopband, but not in both. Okay, and then they're monotonically decreasing in the other, monotonically decreasing in the other. So they have if they have ripple here, they're monotonically decreasing here. If they have ripple here, they're monotonically decreasing there. Okay. And everybody knows what monotonically decreasing means. That means as omega gets larger, the value of h sub a of omega keeps getting smaller. Okay. And there's a difference between monotonically decreasing and monotonically non-increasing. Non-increasing, that means it could remain the same value but not decrease. But when it's monotonically decreasing, it really does decrease. Okay, and then the third category of filters, which we use for a lot of the examples in this course, is elliptic filters. And in this case, you have ripple in pass band and in stop band. So pictorially, h sub a of omega magnitude as a function of omega would look something like that. Okay. So that's really all I'm going to say. Dan, I would urge you, please, in the discussion session, talk a little bit about this appendix and a little bit more details on these filters and the pros and the cons and what their shapes are and what their analytical forms are, etc. I will talk a little bit in today's lecture on the elliptic filter. Okay, next I want to move on to this page. Basically, what you need, this set of specs, they're given to you. You can't really do much about it. So the two things, and this step I just talked about a little bit about how you design an IR, or what are the type of IR filters. I didn't tell you how to design them yet. So these two steps, step number 2 and step number 4, are coupled to each other. In this step, you're transforming the specs from discrete time to continuous time, in other words, from Z to S. And in this step, you're doing the reverse of it. So whatever you do here, you have to undo in step 4. And before coming up with specific proposals of how you do these transformations, I'd like to enumerate some of the desirable properties that you want these transformation techniques to have. Okay, and I'll explain why we want them to have these properties. So desirable properties of transformations. Okay, so there's basically 3 things that we want out of whatever transformation we come up with. One of them, we want a causal stable analog filter to get transformed into a causal stable discrete time filter. And why is that a desirable property? Well, because if I design a causal stable analog filter after I do this transformation, ideally I'd like to end up with causal stable filter. If the transformation transforms a stable filter into an unstable filter, I'm in trouble because I don't want to design unstable filters, right? So that's and if my filter in analog domain was causal, I want in the discrete time domain to be also causal, because that's a nice property to have. So I want causal stable analog filter. And again, I'm using analog in the same way interchangeably with continuous time filter to get transformed into a causal stable discrete time filter. So I want h sub a of s. If it is causal and stable, after I go through the transformation, I want my h of z here to be also causal and stable. That's what that means. The second property is that I want the j omega axis in the S-plane, S-plane meaning the S-plane as in Laplace transform plane, to get transformed into e to the j omega circle in the Z domain. Okay? And why is it that I want that property to hold true? Well, the reason has to do with step 1. Okay? Or rather, step 1 and step 2. Why? Well, because when I'm given a set of specs in the discrete time domain, usually I'm being told what my frequency response has to look like, right? In the discrete time domain. That means in the Z-plane, on the unit circle, I've been told what values should my filter take. Like between this frequency and this frequency, h of magnitude of h of omega should have this much ripple, should be between 1 plus delta and 1 minus delta, and in the stop band, between this frequency and that frequency, it has to take this value. So when I'm given, if I'm given some sort of specs in discrete time domain, in the little omega domain with magnitude of h of omega, I'm usually told, okay, in pass band, you can be between 1 plus delta, 1 minus delta, and in stop band, you can be between, this is omega p, this is omega s, your magnitude can be within delta 2. But what is this? In the Z domain, essentially, if this is the unit circle, I'm being told that, from here to here, to have some certain sort of h of omega has to be between 1 plus delta and minus delta, and let's see. And then from here to here, these are the high pass stuff, and so it has to take different values. So I want this e to the j omega, so this is the e to the j omega in the discrete time domain. I want this circle, after I do the transformation from S to Z or Z to S or whatever the reverse way is, by the time I go to the S domain, I want that to get mapped, this is the S plane, into this j omega axis. This is sigma, and this is omega. Remember, S is equal to sigma plus j omega. This is all from E120, right? Or E20. So I want this circle, e to the j omega, to get mapped to the j omega axis. I want this to get mapped to the j omega axis. And why is that? Well, because that's the only way I can translate these specs in the continuous time domain into specs. Well, my analog filter design techniques work when I have a spec, when somebody has told me what the frequency response of the analog filter should look like. So if I want the specs here to get translated into honest-to-God specs in the S domain so that I can design filters, this circle has to map to this axis. Right?
How can that happen? This unit circle has only magnitude 1, whereas the axis, the magnitude can be.
That's what the transformation does, and you'll see in a minute what potential candidates of transformations are that can do that. Right? Because because in analog domain, at the end of the day, I want to end up with a frequency response spec in the analog domain, and the frequency response. The same way as the frequency in this discrete time domain, the frequency response of a filter is defined by its value on the unit circle. In the analog domain, the frequency response of a filter is defined by h of s evaluated on this j omega axis, right? You all remember that from 120? Yeah? Okay. So the upshot of this thing is we need that. The reason for having, if you can include the top half of this thing. Yeah, so we need this step 2 because need this to translate specs from one domain to another. Okay? So these are desirable properties, and they might not exactly happen, but at least these are the things we would like this to have. So we want e to the j omega to get mapped to j omega. And this is in the z plane, and this is in the s plane. And finally, the last desirable property of my transformation is that I want a rational transfer function in the S domain to transform to a rational transfer function in the Z domain, because at the end of the day, I want to be able to end up with a rational transfer function in the z-domain in order to be able to implement my filter. So you want your rational h sub a of s, or a rational analog filter to get transformed into a rational discrete time filter. Right? H of z. And the reason for that is we want to use difference equations to implement our discrete time filter. And yeah, if you end up designing a nice, good analog filter that's rational, but it ends up being and not having not a rational transfer function, then so what would be an example of a transformation from S to Z that would not do that? So let's say you say, I don't know, Z is equal to square root of S. If you have a transformation like that, it would not preserve this. So we're going to knock out, get rid of possible transformations that are like that. Okay? On the other hand, if you have Z and S be related in a rational transfer function way themselves, in other words, Z is some polynomial in S over some polynomial in Q, if you have a transformation like that, it'll probably hold true, because if you replace, yeah, and you'll see that, we'll see that in next lecture when we talk about bilinear transformation. Bilinear transformation essentially does something like this. So having laid out these desirable properties, let me just make everything concrete and propose an actual transformation. Okay, so here is the impulse invariance transformation as a candidate. And what's the basic idea? The basic idea is this. I have an analog filter H sub A of S, and that corresponds to impulse response H sub A of t. This is all continuous time. I want to come up with a transformation here that gives me H of n. And the transformation I'm going to use is going to be such that I start with H sub A of t, and I sample it at t is equal to n times t, some sampling period t, and that's my H of z. And that corresponds to my H of z. So essentially what this impulse invariance transformation, just like the name says it, I want to make sure the impulse response remains invariant. I want the impulse response of my discrete time filter to be sampled version of the impulse response of my continuous time filter. So that's my proposal. So if I have as a function of t, H sub A of t that does something like that, then I go ahead and sample it at t intervals, and then I get, from that I get an H of n, and that's how I do the transformation. So let's take a few minutes to check to see if this proposal, if this approach, or this transformation, if you will, satisfies those three conditions that we just talked about a second ago. So does this satisfy the desirable properties? Notice that I'm calling it desirable but not mandatory, and you'll see in a second why. So let's just check it over. Question 1 is, does causal and stable H sub A of S translate into causal and stable H of z? Does it or does it not? Well, if I write H sub A of S as summation over k of A sub k over S minus S sub k, I'm just merely writing down the partial fraction expansion, or expanding H sub A of S in terms of sum of a bunch of simple terms, or if you will, this is just a parallel implementation of H sub A of S. Nothing really fancy. So if I assume H sub A of S is of this form, and I assume that this is stable. So assume it's stable. What does it mean for an analog filter to be stable if it is causal? Assume it's stable and it is causal. What does it mean in terms of the S sub k's, for example?
The poles are in the left half plane?
The poles are in the left half plane. That means that if poles are in left half plane, and mathematically that means what? The real part of S sub k is smaller than 0. S sub k is a pole. It has a real and imaginary part. So if this is the S plane, once again, and this is S sub k, when you say it's in the left half plane, this is the real part and this is the imaginary part. That means this is the right half plane here, and this is the left half plane here. So we mean the real part of S sub k has to be smaller than 0. That's the same thing as being in the left half plane. So, okay, we assume that, and let's see if we go through this proposed transformation here, whether that results in a causal, stable, discrete time filter. Well, if h sub a of s is like this, what can we say about h sub a of t? Well, we can take the inverse Laplace transform of this, and because we know it's causal, we know the region of convergence for it, so we know that the answer is going to be a bunch of right-handed things. So that means the from going from here to here, h sub a of t is summation over k of a sub k e to the s sub kt u of t. And here I'm exploiting the causality assumption. Exploit causality. Remember, I'm assuming it's stable and causal in the analog domain. I want to show that with this transformation, it will be stable and causal in the z domain. Now I apply the transformation. If the transformation is any good, it's going to result in an h of n that's also causal and stable. So what is our transformation? Well, it's right here. It says go to the analog filter, sample it at t equals nt. So we do that. H of n is h sub a of t sampled at t equals n times capital T. That's the transformation. And what we get is, well, just replace all the t's with n times capital T in this equation. It's summation over k, a sub k, e to the s sub k, and replace t with n capital T. And then u of t replaced with nt becomes just u of n. Okay. Okay, so that's what the transformation does to an analog filter of that form. First of all, is this new impulse response causal? It certainly is, because it's got this u of n, guys. So this is causal. So we have one check mark. Do you have a question?
It's just that you're assuming that all the poles are distinct. It doesn't assume any multiplicity, because if you do, then probably a t factor will come in. Then you probably have a time varying system.
It doesn't make it time varying. Why would it make it time varying? If you have double poles, it doesn't make a system time varying.
No, but when you say nt, you have, instead of wherever you put e to the power sk nt, you'll have an nt times e to the power sk nt. Is that okay? I mean, I'm just curious about it.
It certainly, that doesn't make the system time varying. Let's agree on that. If the impulse response becomes t times something or n times, the concept of impulse response only exists for LTI system. But coming back to your question, though, does it mess anything up? It doesn't, because even if I have an n times u of n, it still preserves the causality. So you're right. I didn't write down the most general case. I could have put double multiplicities of poles. It would have made this argument a little bit more complicated, but the conclusions would have been the same. Okay? So because the h of n looks like this, it's still causal. So hallelujah, we have one nice property. Now, is this also stable? Is this filter also stable? Well, to check stability, the easiest thing to do is to take the z transform of this. And so let's just do that. So if I take the z transform, I get h of z, and the z transform is a linear operator, so I can say it's a summation over k of a sub k. And oh, gee, this is the easiest thing for us to take a z transform, because it's of the form a to the n times u of n, right? What's a? Well, it's e to the SKT, right? So we know how to do the z transform of a to the n u of n. It's 1 over 1 minus a z inverse, right? In fact, that's the only thing we know how to do the z transform of in the universe, right? So it's 1 over 1 minus e to the SKT z inverse. That's the z transform of this part. Well, is this stable? Well, what are our assumptions? We assume the continuous time filter was stable. In particular, we assume real part of S sub k is smaller than 0. Well, because real part of S sub k is smaller than 0, what can we say about, well, in general, if a filter is stable, if what? In analog domain, if it is already causal for the stability to be true, the poles have to be inside unit circle, right? And what's the pole here? It's e to the SKT. So is this inside unit circle? Well, we have to check the magnitude of e to the SKT. So the question, if this is stable or not, the question is, translates into is e to the SKT magnitude smaller than 1? Is it or is it not? And why is it? That's right. Because the real part of S sub k is smaller than 0, because it's a negative thing, then, and t is a sampling interval, is always a positive thing. So you have e to the power of something negative, and therefore the magnitude of it is always smaller than 1. So because real part of S sub k is smaller than 0, we can conclude that e to the S sub kt is smaller than 1, which means that poles are inside unit circle, which means that we have stability. Okay. So let's just summarize this. We showed two things in this whole analysis. We showed that causal and stable in analog got transformed into causal and stable in discrete time. And also we showed one other thing in this process, and what is it? H sub z looks like this, and what was the third desirable property? We wanted a rational transfer function to map into a rational transfer function, right? So did we show that? Yeah, we started off with H sub a of s looking like this, and we ended up with H of z looking like this. So we also showed that a rational transfer function in analog got transformed into rational transfer function in discrete time. So we showed two desirable properties. And now the last property I want to talk about is the j omega axis. Does the j omega axis map into the e to the j omega circle? Is there a mapping between those two things? So now the remaining question is, could you shift? Oh, okay, I'm going to move myself. Thank you. The remaining question is, does the j omega axis in S plane get mapped to the e to j omega circle in the z plane? And what do you think the answer to that is? Anybody? No, actually, you should know the answer to it precisely. In what way? This is my transformation. Stare at it. Where is it? Page... here. This is my transformation. I'm just sampling my h of n at equally spaced points. So, do we know how this frequency response h of omega is related to the continuous time frequency response h of omega? In general, if I have a continuous time function and if I sample it at t, which is what I'm doing there, do I know the relationship between those two Fourier transforms? Yeah, that's the first thing we did in the class like 9 million years ago at the beginning of the semester, right? And what is that relationship? That's like old news almost. What is that relationship? Well, if I'm doing h of n is a sub t, if I'm sampling this, then I can say that h of omega, the discrete time Fourier transform of this, is the replica of this thing summed over, right? It's 1 over t summation over r h sub a of omega over t minus 2 pi r over t. That's the thing from beginning of the class, beginning of semester. So can I easily then, so what does it mean pictorially? Well, it means that h of omega as a function of omega, if I were to plot it, is these h sub a's. Just repeat it. Right? And so can I then, if I have some sort of specs in the discrete time domain, can I translate it into h sub a? Is there a one-to-one mapping? Is there one-to-one mapping between the specs in the discrete time domain and analog domain? There could be if there's no aliasing. So there could be. So can I translate? The question is, can I translate the specs? And the answer is there could be if there is no aliasing. Okay. Or if the aliasing doesn't interfere quite a bit. And what if there's a little bit of aliasing? Well, then in translating my specs from analog domain to discrete time, from discrete time to into the analog domain, I didn't exactly translate it. There's a tiny bit, I'm a little bit off. So what does it mean? That means if I design my filter in the analog domain that satisfies the specs, by the time I translate it to the discrete time domain, it could be a little bit off. But does the technique entirely fail? No. It doesn't entirely fail. If I'm off a little bit, at the end of the day, I might still satisfy the specs anyway. Or I might be able to jack up the order of the filter just a tiny bit to make up for the fact that the spec, for the little aliasing that was introduced. It's not a total disaster. It's just a little bit inconvenient. The same way as window design was inconvenient because we could never be 100% sure that we satisfy the specs. So to put all of these things in perspective, let me just give an example of analog filter design using the impulse invariance technique. So to make all of these things a little bit more concrete. So here's as an example. Design using impulse invariance. Okay. And by the way, I might need a textbook, which I see there's one here, to show some pictures. I did not bring mine, but let's just go over the example. So suppose I'm given this set of specs. And the specs are in discrete time domain, not analog. And I want to design a low-pass filter. And it goes something like that. I have a magnitude of h of omega. It has to be between 1 and 0.89 in this region, all the way to omega equals 0.2 pi. And then from 0.3 pi on all the way to pi, I want the magnitude to be no more than 0.177. And this is something that has come up because you designed your system, somebody gave it to you, etc. So I want magnitude of h of omega to be smaller than or equal to 1 and 0.89 for omega between 0.2 pi and 0. And I want the same thing to be smaller than 0.177 for omega between pi and 0.3 pi. Okay. So that's step 1. Somebody has given us the specs. Step 2, we want to translate these specs into continuous time space. Okay. So step 2, translate the discrete time specs into continuous time specs. And how do we do that? Well, let's just choose t equals 1. And I'm going to make a claim that 99% of the time when I teach this course comes across as extremely anti-intuitive, and I spend a lot of time convincing people that it's true. I want to claim it doesn't matter what value of t I pick. I can pick 1, I can pick 2, I can pick 3. As long as I choose the same t in step number 4 of the filter design, when I go back from, here's step number 4, when I go back from S to Z domain, I always get the same answer. And students always get tripped on that. They say, really? You know, I thought this t matters and it makes a difference. It just doesn't. You can pick it equal any value you want. As long as you're consistent, and in step number 4, you use the same value of t, you get the same answer. But let's just do this step. So if t is equal to 1, so when I do this transformation, how can I translate the specs from discrete time to analog? Well, my h of omega is supposed to have this set of specs here, and I pick t equals 1. That means there's absolutely no scaling of the omega axis is going on. And that means, remember, there's a scaling factor of capital T between little omega and big omega, right? Remember that from way at the beginning of the class? If I pick t equals 1, then little omega becomes the same as big omega, and the specs translate exactly. In other words, my specs in h sub a of omega is going to be identical. It'll be between 1 and 0.89 for capital omega naught to 0.2 pi, and from 0.3 pi all the way to infinity. Remember, capital omega doesn't have a pi thing to limit it. It goes all the way to infinity, right? And it's going to have to be 0.177. So because I picked t equals 1, just omega got translated into big omega. So this becomes my spec in the continuous time domain. And if you pick t equals 2, there will be a scaling factor. This would become 0.2 pi divided by 2, 0.1 pi, and this becomes, everything gets scaled. But we just, for convenience, we pick t equals 1. So now let's go to step number 3. So here we translated the specs, and go to step number 3, design the continuous time filter that satisfies this spec. Okay, so we're going to design a Butterworth filter, which is monotonically decreasing in stop band and pass band. And how are we going to design it? Well, because Butterworth filter is monotonically decreasing, it just does that. And ideally speaking, you want to design a Butterworth filter of a very low order, right? The same way as in FIR filter design, you want to minimize the number of coefficients, so you minimize the amount of delay and the amount of computation you do. In IIR filter design, in continuous time and in discrete time, you want to make sure you design the lowest order filter that satisfies your spec. Because if you have a high order filter, that means you have a lot of A of n coefficients and B of n coefficients, like I talked about here. You want this order n to be small so that you have minimum number of delays and summers and adders and all those other junks, right? So you want a low order filter. Anyway, to design a low order filter, given that Butterworth filter monotonically decreases like that, what is a good set of constraints I can impose on my Butterworth filter? Well, a good set of constraints is to make it do this, is to have it start here and to have it go through this point and to have it go through this point and go down. In other words, impose for my Butterworth filter to pass at 0.2 pi, to pass at the 0.89 value, and to impose that its magnitude at 0.3 pi is 0.177. Why is it a good idea? Well, if I have it do this instead, for example, right? If I have it go through not this point but something higher up, but still in the spec here, and not through this point but something lower down in this range here, it will have to have a sharper transition in the same frequency range, i.e. between 0.2 pi and 0.3 pi. It has to drop more values. Here, from red to red, it only drops this height. From blue to blue, it would have to drop this height, which is larger. So if in the same transition width, it has to drop faster and larger, what would it result in? It's a tighter spec. It's a more difficult spec. The more brick-like your specs are, the higher the order of the filter to satisfy that spec. And we want to avoid having a high degree filter. We want to come up with the lowest degree filter that does the job, right? For those reasons, in order for me to design my filter, I'm gonna be the laziest as possible. In other words, I'm gonna put the minimum amount of constraint on my filter, make it have the least amount of drop. So I'm gonna force it to go through the lowest point in passband and the highest point in stopband. Okay, is that point clear? Okay. So let's come back here. So to summarize here, my goal is to, I'm going to use a Butterworth filter for one thing, and to minimize the order, I will impose the following. I'm going to impose so that magnitude of h sub a of omega at omega equals 0.2 pi is smack the lowest value I'm allowed to be, which is 0.89. I'm also going to impose that the magnitude of h sub a of omega at omega equals 0.3 pi to be also smack the highest value it can be, so that I minimize the transition. I minimize the amount that this thing has to drop in that 0.2 pi to 0.3 pi region. Okay. So what does that mean? Well, what do I know about Butterworth filters? I never explained anything about them. I think I skipped 2 pages now. But now is time to give a 2-minute tutorial on Butterworth. Not margarine worth, but Butterworth of order n. How does it look like? Well, what we know about Butterworth filters is that magnitude squared of a Butterworth filter is of this form: 1 over 1 plus omega over omega c to the power of 2n. If I have a Butterworth filter of 2n, the magnitude squared looks like this. And omega c is generally referred to as the cutoff frequency, and n is the order. So, and pictorially, so as if I plot h sub a of omega, it's not only monotonically decreasing, but if I plot it like that, as n increases, I'm going to be able to make the transition sharper and sharper. So this is n large. As n gets larger, I can make this thing to become sharper and sharper. Right? And where do the poles and zeros of this Butterworth filter look like? Yeah, can you include this top? Yeah, great. So for a Butterworth filter, so this is a tutorial on Butterworth. So how do the poles and zeros of this thing look like? Well, here's how it looks like. This is the S plane, this is sigma, and this is omega. Remember, S is equal to sigma plus j omega, all the way from 120. So the poles of this guy are on a circle of radius omega c, and my apologies for not being able to draw a good circle. And if I have, let's say, for the sake of example, n equals 6, then can you go up just a tiny bit? And then this guy is going to have 12 poles uniformly spaced around this circle. So 360 divided by 12 is 30. So there's 30 degrees apart. and I'm going to have 12 of those, but but this is magnitude squared. The actual Butterworth filter only has the poles in the left half plane to make it stable, right? So let's put 12 dots around this circle, and each one is 30 degrees apart, right? So it'll be here, 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 or maybe here, not that one, and here. Okay, so these are all 30 degrees apart, okay? And the Butterworth filter is the filter, the poles of the Butterworth filter are all the ones on the left-hand side. Those are the poles of the Butterworth filter. So they're 30 degrees apart. Okay? So what can I say about, so this is all the tutorial I was ever going to do on Butterworth filters. So coming back to, all right, so coming back, end of tutorial, coming back to this equation here that we have, okay, so we decided to, back to the example, we wanted this guy to pass through, remember, we wanted h of omega to pass through this point, and that's how it got translated. Now that we have a nice expression for Butterworth filter that looks like this, we can plug this in and write that down. So what can we say, combining this guy with that guy, what can we conclude? Well, we can say that h sub a of omega squared at omega equals 0.2 pi is the same as 0.89 squared is the same as this thing, which is 1 over 1 plus omega over omega c to the power of 2n. Oh, I'm sorry, omega evaluated at omega equals 2 pi, which is 0.2 pi. Instead of omega, I put just 0.2 pi. Because I'm using a Butterworth filter, and that's the expression for a Butterworth filter. So that gets translated into this, and this second one gets translated into this. H sub a of omega squared at omega equals 0.3 pi is equal to 0.177 squared is equal to 1 over 1 plus. Now what's the omega here? Well, we're evaluating at 0.3 pi, so replace this omega with 0.3 pi over omega c to the power of 2n. So these two specs from up here got translated into these two. They're not specs really. Those are that's the fact that it's a constraint that we imposed. We decided that our h sub a of omega has to pass through this point and that point translates into that. So now what do I have? I have a system of two equations and two unknowns. It's not really a linear system of equations, but even if it is nonlinear, because there's so few unknowns and so few equations, I can just solve it in some sort of a numeric way. So I can say two equations plus two unknowns. And what do I get when I solve this? I get n equals 5.88 and omega c equals 0.704. And because n is the degree of my Butterworth filter and it has to be an integer, I'm going to round that up to n equals 6. So n equals 6 and omega c equals 0.704. Well, I'm sorry. So you got n. So you increase. Sorry. So you increase n equals. You increase n to 6. Okay, because you can't have. You round it up because 5.88 is so close to 6. We picked n equals 6. Now, I could use n equals 6 with this omega c, but that's an overkill, right? So I have to somehow figure out what the new omega c is. And I have two ways of doing this. What are the two ways? I can either, looking at here, I can either plug n equals 6 here and compute omega c from this equation, or I can plug n equals 6 here and compute the new omega c from this equation. And which one do you think I should do and why? Well, think of it like this. In this picture, if I plug n equals 6 into this equation and compute omega c, I'm going to be enforcing that at 0.2 pi I pass through 0.89. I pass through this point. If I plug n equals 6 here and compute the new omega c here, I'm going to be enforcing that at 0.3 pi I pass through this point. The fact that I've jacked up my n from 5.88 to n equals 6 means I'm somehow over-satisfying the specs or something. So in your mind, which is a better way of over-satisfying the specs? To pass through this point and go a little bit lower here, or to pass through this red point and go a little bit higher up there? And why?
It really depends on whether you need a flatter passband or a more rejection in the stop band.
Yeah, but it also depends on something else that I talked about, which was the aliasing argument. If you don't want to have aliasing, or if you want to minimize aliasing, remember I talked about that a few minutes ago? You want this thing to die down, right? So it's better for us to satisfy the spec here and over-satisfy it in this region to minimize the aliasing so that the transfer between the S and Z domain remains intact. Remember this picture we had? Remember this thing? Right? We want the H of A that we designed to die down in the stop band as fast as possible, so to minimize this aliasing. Okay? So to summarize everything, and I realize I've gone over time, but it would have really taken too long to get to this point in next time's lecture. So we have two choices. Okay, choice one is either, we call this equation 1, and we call this equation 2. Either use equation 1 to compute omega c, or use equation 2 to compute omega c. And what I'm claiming here, what I'm arguing here is that so here's equation 1, here's equation 2, so that if I use equation 1, then what's going to happen is I pass through 0.89, and in the stop band I'm going to do this. Okay? 0.3 pi, 0.2 pi, 0.177. If I use equation 1, I get that. And on the other hand, if I use equation 2, I get the opposite. So in here, I am over-satisfying the stop band. Okay? And here, if I use equation 2, I satisfy the stop band, but I'm over-satisfying the pass band. So here, over-satisfying the pass band. And what I'm claiming is that I'm going to choose this thing, choose this, to minimize aliasing. And once I do that, so then I just plug it into equation 1 up here. I compute the new value of omega c, and I'm done. Essentially, I'm done. Okay, so so let me just wrap up here. So use equation 1. Then you get omega, you compute the new value of omega c, which ends up being, so use equation 1. That means I'm going to say 0.89 squared is equal to 1 over 1 plus 0.2 pi over omega c to the power of 12, because we already choose n equals 6. And that results in omega c equals 0.7032. So bingo, I'm done with step 3. I designed my analog filter. And I will continue this discussion on Friday. So as long as you come out with a filter and after you transform it back, you satisfy the specs, you're done.
But what
it doesn't matter whether it's one or not.
Oh, okay. So my second question is, let's say...
But when we do bilinear transformation, it will be 1-to-1.
Okay. My second question is, if I have a circle, and then I map it to a straight line, right? And then when I map the straight line back to a circle, instead of using the same T, I use a different T such that, do you think it will be a rotation in theta as a net effect?
Rotation in what?
In the C plane, so that I can make a, let's say, band pass filter or maybe high pass.
I have to think about it, but you should certainly use the same T in going back. Okay. For this discussion, if you use T equals whatever 5 in one way, you have to use the same T to find back.
So so is it possible, maybe in general, is it possible if I map the C unit circle to a straight line, then when I transfer back from the axis to circle, instead of having the same original unit circle, I have some sort of rotation?
Why would it be a rotation? I'm not quite sure why you come up with...
To do something like this?
It's possible, but whether or not the technique would work and you get a useful filter, I don't think so.
I can